Okay, hello everyone. Welcome to the SEPM Deepwater Research Group meeting. We're very excited to have everyone here. We've got a great list of talks lined up today from all over the world with a range of experience from the speakers and from a range of different topics from subsurface to outcrop and to modeling. It's my pleasure to kick this off. My name's Stan Stanbrook. I'm a deepwater stratigrapher, and I'm here with the rest of the Deepwater Committee, Fabian, Emma, and Lydian. I'm going to hand it over to Fabian to talk us through what's going to happen in this event.
Thanks, Dan. So again, thank you everybody for joining. I know we have people joining. It's the morning for them, it's the afternoon, and it's the evening. So again, thanks for everybody taking the time to participate in this. So welcome to the 2024 Deepwater Research Group meeting. The theme of this year's meeting is complexities and heterogeneities in deepwater systems, looking at new approaches and challenging old ideas. And what you can see on the slide that is being shared here is we have a range of topics, right? We're very lucky to have a diverse group of presenters and speakers and panelists that are going to be walking us through sharing their research on understanding concepts and processes and controls in deepwater sedimentology and stratigraphy, leveraging outcrops to further understand some of these processes and apply our thinking to that. Then we're going to be stepping into better understanding the subsurface, applying these workflows into the subsurface, leveraging tools like machine learning and numerical modeling to again kind of look forward in terms of what we can do to integrate all this work. So as Stan said, we've got a multitude of perspectives that are coming from this. In terms of the layout or the breakdown of what we're going to be going through today, we're going to have about three to four longer talks, about 15 minutes each. Then we're going to go to 2 shorter talks. And then we're going to take a time for questions that we can have there, and we'll be throwing polls actually throughout the presentations. And then we'll take a break. Then we'll actually come back for another round of 5 to 6 presentations, longer and shorter ones as well. In terms of the questions, the way we're going to be doing it is please feel free to add questions, throughout on the chat. And Stan and myself, Lillian, Emma, we will be fielding those questions and asking them as possible. The benefit of also placing them in the chat is that we can actually save that, so we can actually send them out to all the presenters after this. So any questions that aren't addressed during the actual presentations, because as we have a lot of material, we'll send it to the speaker so they can kind of answer them in addition to that. I think we can go to the next slide, Stan, here. So, please remember all that, during this presentation, again, we thank everybody for being here. All SEPM activities, we want to follow the SEPM code of conduct, and we're asking all the participants to abide by that code, to abide by the code of mutual respect with everyone. So please do be respectful during the in-person, events that aren't happening today, but the online ones that are happening today. And again, let's just, be excited and be respectful for the range of diversity in terms of what's going to be presented today and all the presenters and attendees that we actually have as well. I think that's kind of it from my end in terms of like breaking down the details. I don't want to take up too much time away from our presenters, but yeah, I think we can move to the next slide. It's not moving on my end here. I think you might have to. Yeah, it's not moving on my end here. Maybe that's my computer.
Okay. Well, so the next slide is simply a little bit of guidance to the audience, hopefully, or who are seeing the slide, on how to be able to enter questions into the system, the webinar system here. It's simply a case of typing in towards the bottom of the screen underneath where it says questions, and then you can hit send. Note you may have the option to send the question to the staff or to the entire audience, so be careful which one you select. If you want to raise your hand to ask a question, you can do that, but do know that our intention is to field the questions for you. So you're probably better off just putting the question into the chat.
Absolutely.
I think
all
with
right.
that, we go to our first presentation, Cassie.
Yes, so we will be going to our first presenter. That's Kevin Pickering from University College of London, who's going to be talking about, diving into deep water depositional systems, understanding those controls and those mechanisms.
Okay, thanks, Dan. Thanks, Fabian. Can everybody see my screen?
We can.
You can. Good.
Yes.
Well, Fabian said we're going to walk you through a whole bunch of things tonight, this afternoon for you guys in the US. I'm actually going to race you through them, but I have a couple of really simple points. And what I've done is I put the references to everything I'm going to talk about on the slides so you can follow them up if you want in your own time. So I'm not going to feel too bad about going fast because the information is there on the screen to look at in a more leisurely way at a later time. So what I want to do is to look at drivers on deep water depositional systems, the controls and timescales, and I want to sort of be provocative, and I want us to think about sort of what we know, what we think we know, what we don't know, and maybe what we could do in the future. And I'm obviously going to take my experience to drive us through this. Well, on a very large scale, we all appreciate that submarine fans take quite some time to deposit sediment across ocean basins in quite a complex way. This is from a paper in 2019, Sedimentology, and it shows the Bengal Nicobar fan in stages from 30 million years to the present, with India reconstructed moving northwards over that time. The 90 East Ridge is the diagonal line in the middle there on the blue colored ocean plate. And what you can see, the dark yellow are the coarse clastics and the lighter yellow are the siltstones, mudstones, mostly silty sediments. And you can see that through time, where the fan is most active changes. And eventually at around about 2 million years, the 90 East Ridge impinges on the Andaman island area and therefore cuts off the Nicobar fan, which is a very impressive fan. So on a very large scale, we need to appreciate that at continental margins, deposition is extensive and complex and in some ways compartmentalized by tectonics, with obviously other processes on the way. Now also, something else we can do when we look at these longer term trends, this is a paper published just before Christmas, looking at the evolution of the C3, C4, well, the C4 grasses, and that's the abstract, that's the paper, you can follow that up. But this is the key figure from that paper. You can see over 10 million years, the fraction of terrigenous organic matter from the C4 source. You can see that there's a big kick at around 7-ish million years ago, and another one at around about 2.5 million years ago. And this is related to the C4 grasses, and the arguments, which you can check up in the paper at your leisure, are that the monsoons are probably intensifying at those time periods. So we can kind of look at controls on a very long time frame, the evolution, if you like, of the monsoonal system over a large fan system. And that's all I want to say about very long-term trends. We also know, look at Taiwan, this is from Liu et al. In 2013. If you look at the lower graph, the discharge in cubic meters per second in time in years, those three yellow circles with KF and M on are very large storm events, typhoon events, with very large input of sediment through the system because of it. So we can see that on short time frames, having looked at very long time frames, we can see that typhoons can release extremely large volumes of sediment into the deep sea through the river systems. Well, in 1999, so a long 25 years ago now, I was interested in whether active plate margins would reveal a Milankovitch control on sedimentation. And so with a whole bunch of colleagues and a PhD student of mine, we undertook a planktonic foraminiferal study using delta oxygen 18, delta 13 carbon records from about a 600,000 year time period in Japan in the Kazusa group and the Afro Basin. And the argument was, if you can pick as tectonically active areas you can find, will you see a climate signal or a tectonic signal? Well, now we kind of know the answer to that, but I just want to sort of put this in perspective. So from that work, this is the graph, one of the graphs in the paper. The yellow are the sand bodies, that's 600,000 years of time, and the blue are the glacials, and the white are the interglacials. And this is based on correlating the data from the Kazusa group with the open ocean signal. So we're very confident that those are the glacial interglacials. And what you can see is the yellow sand bodies are pretty well coincident with the glacials, not every single time, but it's a pretty good fit. So it's hard to believe, but we were surprised by that 25 years ago. But now I think many people would accept that glacial interglacial cycles can drive sediment input into the deep ocean at Milankovitch time frames. Well, a couple of other points before I go into the Ainsa Basin. This is from Armitage et al. 2013. I want to remind you of 2 points here. One is from this paper, and that is that the landscape evolution suggests a timescale of sort of 10 to the 6, really, a million years, whereas Milankovitch forcing 10 to the 4, 10 to the 5 for the precession, obliquity, and shorter eccentricity. And the results of the modeling by Armitage et al. Was that they suggested that stratigraphy built by particulate fluxes from upland catchments and long-term trends in sediment ocean were probably relatively insensitive to short-term climate variability. So in other words, this was an argument for tectonics and landscape evolution. Another paper of importance around about this time, Blöther and Kurup, 2013, they, and I've just picked the key point out from the abstract here, they showed that Himalayan valleys could store sediment for 1,000, even up to 100,000 years. And so there's some lag effect here between delivering the sediment into the deep ocean, a hysteresis effect, if you will. And they concluded that it's likely that sediment routing systems may sufficiently buffer signals of short-term seismic as well as climatic disturbances to complicate any simple correlations. In other words, you'd be surprised to perhaps get a good Milankovitch cyclicity from deep sea sediments in the deep ocean from the Himalayan system. Remember, that's a very big system. Okay, now I want to race through the Middle Eocene in the Pyrenees, because I think most of you are familiar with it, and then get to a couple of simple points. Well, the first thing is we needed a geological map when we started working there. And the whole point of my work with my students there was to try and understand what's driving systems more than anything else. And there are 2 papers there from which we produced maps. That's one of the maps. And you can see it's a syncline plunging south. The colors, the brightish colors are the sand bodies. The blue is the mudstones, and the mauvish colors are mass transport complexes. Anyway, that's about 4 kilometers, 3.5, 4 kilometers of stratigraphy in about 9-10 million years. And we needed an age model. So we produced our first age model in 2015, which we've developed since. But I just want to pay respect to the people who produced the first age model. Well, going around the Ainsa Basin, this is quite a large outcrop. You can see this section of milestones and very thin-bedded turbidites, mostly thin-bedded. And if you look into that cliff there, you can pick out around about 4 fairly clearly defined packages at around about 5 meters or so thick of more abundant sandstones. And these are not the sand bodies. These are within, well, they are sand bodies, obviously, but these are within the marl sections. And this got us thinking, well, can we identify Milankovitch cyclicity in these sections by using spectral gamma ray logging, geochemistry, whatever. So that was sort of the impetus for really starting to look. We identified Milankovitch forcing in bioturbation intensity, Hurd et al., and we identified the obliquity and eccentricity cycles in that. In the lower paper, we looked in detail at spectral gamma ray logging and bulk sediment geochemistry and identified precession and obliquity cycles at around about 10 and 6 meters. So that would be, those cycles would be around about 6 meters. Then we went on in detail to do a lot of work with Blanca Cantalejo in fine grain sediments. We used a multi-proxy approach to look at our 230-meter core that we drilled in the Yaitse Basin, and we looked at 150 meters of that using multi-element scanning. We identified Milankovitch frequencies at the precession, obliquity, and eccentricity, short eccentricity. So orbital parameters did appear to be important in controlling sediment delivery of the deep marine system. We then went on to look at the entire stratigraphy and pick all the best sections we could find for high resolution spectral gamma ray logging. And within that, so about 1.4 kilometers of stratigraphy measured, we identified Milankovitch forcing throughout the basin. So we'd gone from a small scale up to the basin entirely. And then from that, and remember this is all the fine grain sediments, then what we wanted to do was to try and look at sand bodies, because there's about 25 significant sand bodies, 8 depositional systems. This is just a panorama showing you some of those sand bodies, the Yaitse 1, 3, Murillo 1, and Guaso fans. So there are other systems in there, but they're not so clear to pick out from that photograph. And around about that time period, Casteltorta et al., they looked at the carbon isotope stratigraphy in the basin, and they showed that the sediment gravity flow deposits in place, sandy systems in place during the static low stands, and the fine-grained intervals during high stands. So basically, they supported the sequence stratigraphic paradigm for high and low stand systems. This is a diagram from one of the papers, 2017, and I just want you to focus on the arrow system down there, the arrow sand body, or arrow fan as I would call it. You can see there they looked at the bulk carbonate, for example, and that's shown alongside that sand body. They then looked at the sea level curves that were available, published, to look at whether that arrow sand body might be deposited during a high or low stand. It was perhaps entirely tectonic. Well, I mentioned they looked at bulk carbonate. We also looked at bulk carbonate, and this was a problem for us. This is just a pilot study from the youngest Guaso system. And if you remove the 3 outlying points on the right, you end up with a very high correlation coefficient between the delta 13 carbon and the delta oxygen 18, which suggested to us that there's a strong diagenetic signal, and therefore we were not so keen on using the bulk carbonate as is used here. So that's why we didn't pursue that further. We then revised our age model in 2020. That's the paper that did it, and that's just some verbiage from that paper. We also, in 2020, with Connell from Oxford and others, we looked at the pacing of the sand bodies in a paper with, and Ken Miller was co-author as well, and we reckon that about 72% of the sandy fans are potentially coincident with the long eccentricity of 400 km minima, and therefore potentially record climate change. So that's kind of a similar result to Casteltorta et al. So that was our stratigraphy there in the middle, sea level curve on the right. This sea level curve is obviously published now, it's in our paper, but until this was published, people would be using sea level curves from Miller and others that go back quite a bit older than this. And this is a 5-point moving average. And on the left there, we used our gamma ray logging to tune it to the orbital solutions of Lasker et al. 2011. And then you can see the eccentricity on the left, and then the 400,000 year cyclicity, the longer eccentricity in the middle there. And the key point here, and this is the simple point I want to make, if you look at the arrow sand body down there, way down the bottom, you can see that this corresponds with quite a pronounced fall in sea level, which is the complete 180 degrees different to the previous paper. So I don't have time in this talk to go into the details of the methodologies, but my point is a simple one, that with very high resolution stratigraphy, you can end up with diametrically opposed results. And obviously it's to do with how you fix as accurately as you can the timing of the sand bodies. And I'm going to say to you that accurate as we can be, you can't be that accurate still, because you're really trying to understand stratigraphy at the 20, 40, 100,000 year cyclicity when your errors are large enough to move you through several tens of thousands of years anyway. So another paper published a couple of years ago, Lacustrine et al., they showed that most sand bodies were deposited during sea level falls, and this is using their data, bulk carbonate, and a lot of other data alongside the published sea level curves. So again, there's a kind of a convergence, a consensus that falls in sea level probably are when most sands were accumulated, but there's disagreement when you start to look into individual sand bodies. So this was a figure from their paper, and I've just put in the green box here. You can see again the arrow SGF, the arrow sand body is shown there at the upper of the two grey lines, and you can see on the sea level curve from Miller et al. 2005 and Comets et al. That it's shown against a sea level rise. So there's a problem there. And I just put our data back on again with the arrow sand body showing it against a fall rather than a rise. Well, I'm going to leave it out there for you to think about and to decide on what might or might not be true. But some essentials: understanding temporal controls on deep water systems needs to be reliable and reproducible. Remember, as scientists, we shouldn't feel that if somebody's done a big detailed study in a basin, that's the answer and you're not going to bother. Things should be tested. And I'm going to suggest that those young field interested people out there listening should maybe think about going back in and redoing, testing our studies to see with maybe new proxies if possible, to see what might be most likely. Obviously, you need to determine the nature of sedimentary systems from source to sink, the routing within the basin, temporary storage, hysteresis effects, I touched on those, Himalaya, and then your receiving basin bathymetry, which might divert sediments off into the basin. And the devil is always in the detail, and that's really the point of this talk. Further research, continue to investigate greenhouse versus icehouse, and try and get some understanding of sea level response for differing rates and magnitudes of sea level change and amounts of ice cover. And don't forget, thermal expansion and contraction of the oceans will also affect sea level and therefore potentially sediment delivery. Please compare different deep moving systems in different tectonic settings. These are fairly obvious points. Develop perhaps new proxies for environmental change. Continue to research the sediment response to seismicity, a range of magnitudes and timescales. Compare river attached versus river detached submarine canyon fed systems. And finally, appreciate that searching for a single principal driver on deep water depositional systems is likely to be fruitless. In fact, probably is fruitless. But determining the main driver is possible, as I hope I've sort of indicated. So understanding the heterogeneity of deep water systems is only possible with detailed, reproducible land and deep water maps, robust age models, and an understanding of the processes involved. So a very simple point from quite a race through the topic. And by the way, I just point out that in Ainsa, in the Pyrenees, we have a core lab in the Dos Rios Hotel. That's just a picture of it. So if you're ever in Ainsa and you want to look at the A6 core, which was a fine grain core that we studied, and other cores, then you can do it there. So thanks for your attention.
All right, sounds great. Kevin, thank you so much for that presentation. And I think it's, I really like the points that you made at the end towards, you know, in terms of understanding how our processes, our understanding of our processes could be, you know, they're impacted and they change when you actually consider the timescales at which we're operating. And I think that's kind of a nice, you know, lead into the fact that, you know, we have to approach deep water from diverse perspectives. And so we're now going from Spain to Namibia, from the Eocene to the Neoproterozoic, where Nora is going to be giving us an awesome presentation on submarine fan heterogeneity in the Neoproterozoic Xerocene deep water fan system in Namibia.
Great, thank you, and thank you for the introduction. Can you see my screen?
We can. It looks like it's, you might need to swap the display thing.
Okay, great, thanks. How's that?
Perfect.
Perfect, thank you very much. So with that, thank you very much to the committee for organizing this event. and for inviting me to talk today. I will be talking about submarine fan heterogeneities in the Zaresna deepwater fan system in Namibia. And I will also be touching on the implications of recognizing heterogeneities in deep water deposits more generally. So I'll try to squeeze that in. But first I want to acknowledge my co-authors on this work. They are Tim McCard, Jared Gooley, Andrea Fildani, and Don Lowe. I also would like to extend a special thanks to Roger Swart, who introduced Don and I to the field area initially. And then additionally to some characters who either visited us in the field or helped with some field work, those being Kai Kutafabricus, Bill Morris, Dominic Armitage, and Matt Malkowski. And for some context and perspective of the Neoproterozoic Zaresna group, this is an ancient deepwater system with unparalleled exposure in the Damara region of Namibia. These outcrops are arguably the most laterally extensive deepwater deposits in the world. This map is a Google Earth image of the entire exposure, all of which are vertically dipping beds with no vegetation cover. The Zaresna group records intensely folded and metamorphosed rocks. You can really come to appreciate that in this tight folding with a simplified geologic map of 5 units that make up the Zaresna group, each of which is tightly folded and thus repeated across the entire exposure. So each of the north-south ridges that you can see on the Google Earth image is representing an exposed portion of a fold. The Zaresna group comprises these 5 units, all representing deep water deposition. There are 3 siliciclastic units interbedded by 2 carbonates, which are snowball earth cap carbonates. And then here finally is an image of the character of the exposure and just the sheer size and extent of the exposure on the ground. To provide you with a simplified, very quick geologic setting for the Zaresna group, we first start near the time of spreading of Rodinia. Note that this cross section takes a 90-degree turn at point B to show that with the opening and spreading, there were 2 ocean basins that opened up. Sediment initially started shedding off the Congo Craton into the deep water basin, and then with additional contribution from the emergent coastal terrain, until ultimately the basins closed and deposits were significantly deformed, and as we see them today, with the suturing of Gondwana. So the Zaresna group was deposited in a deep water basin near the junction of these 2 oceans, sometime between the rifting and spreading, and then ultimate subsequent continental collision. So now the rest of this talk will focus on work that was recently published and focused just on the middle siliciclastic unit of the Zaresna group, and that's the Brock River Formation. So on the bottom is a view looking south from a high point in the outcrop that's located at the very northern tip of the black rectangle on the map. This view is looking down stratigraphy, again with vertically or slightly overturned dipping beds, and with stratigraphic up in this image to the right. And this is an area where one can, and we did, walk out deposits. You can walk out turbidites for just about 12 kilometers in this single fold limb. And here I also highlight the character of the Brock River Formation, which in this locality, the lower and then middle and upper Brock Formation are separated by really thick mudstone dominated intervals. You can kind of see as those valleys in between the turbidite beds. So given the exposure, the structural dip of these outcrops, the stratigraphic sections that are measured on the ground can also be overlaying on aerial or even satellite imagery, as you can see here, to help trace out beds or bundles of beds. So this time, the stratigraphic up is to the left in this satellite image. And once again, you can see those mud stone dominated intervals really clearly in between the lower, middle, and upper Brock. The ability to have such high confidence in correlatability and to be able to walk out individual beds and individual turbidites in some cases provides a unique opportunity to answer some key questions about the deep water system and deep water fan systems more generally. So these include what's the lateral variability, what's the heterogeneity of these deep water fan deposits, what's the spatial distribution of the facies, and what's the temporal evolution of the whole system, of the fan system. To answer these questions, we started by measuring repeat sections, stratigraphic sections in one fold limb, the fold limb I keep showing you. And here in the bottom panel, you can see actually where those 5 sections were measured in small drainages in the outcrop where the rocks were best exposed, and where each of these beds measured in these sections could actually be walked out between the sections. Beyond that, we took advantage of the folded, repeated nature and stratigraphy throughout the region to measure more sections across the basin. So from centimeter scale truly to basin scale. These totaled in 10 sections, and these are all repeated sections throughout the same stratigraphy of the Brock River Formation. Now, the most reliable correlations are those within the same fold limb. Like at the very eastern part of this map, in that copy location, are the 5 sections that I showed you earlier. But then identifiable markers, such as those mudstone-dominated intervals, can be identified across fold limbs and used as datums to correlate stratigraphy. Additionally, the fact that the Brock River Formation is in contact below and at the top with 2 different carbonate units really helps identify datums as well to correlate stratigraphy across the basin. So before jumping into that investigation of heterogeneity, I wanted to first briefly introduce our hierarchical scheme for the Zarestina group, which is largely based on other deep water lobe schemes, but tailored for this set of rocks. The building blocks really start with bed divisions based on sedimentary structures and flow type, beds or sedimentation units, each representing a deposit from a single flow, and sedimentary facies or mappable groups of genetically related beds. And then ultimately facies associations. But on this slide, I'm focused on 6 sedimentary facies that were identified in the Zarestina group. And then I'm showing some just representative photos of all 6 of those. And then those grouped together stacked to form what we interpreted as facies associations, of which there were 4 shown here in stratigraphic section. And next to the lithologies in the strat sections, you can actually see those previous colors of the sedimentary facies from the previous slide. And the important part with trying to put this basin in context and evaluate the behavior of and stacking of these deposits is in the hierarchical scheme, correlated facies associations are interpreted to represent deep water lobe deposits. So when these are correlated between sections, there's a consistent pattern of FA1 to facies association 2 and 3 that helped us identify and interpret the axis or off-axis fringe or outer fringe of lobe deposits. And so it's really these that allow us to correlate and identify geometry of lobe deposits across the basin. So to show you that in outcrop, at the very bottom is a stratigraphic section laid on its side. So at the very, very bottom is the stratigraphic section. Then there's a thin column above that with more colors, and those are the stratigraphic sedimentary facies, excuse me. And then above that, at the very top column are colors that show the facies associations. And essentially we can drape those over and correlate across the outcrop. And these are lobe deposits that then can be traced out over longer distances. So to show that back in that original fold limb that I introduced you to earlier, here are correlations between 5 sections at that lobe deposit scale that again have been walked out to cross-check with boots on the ground. And beyond that, it's jumping and scaling up to the basin scale, as painful as it is to squeeze in centimeter scale detail of each of the sections onto a slide like this. Here are all 10 stratigraphic sections through the stratigraphy. Now, You'll notice the 5 sections that I just showed on the previous slide are all the way to the east and the bottom right. And there are 2 sections in the whole area that were measured through the entire thickness of the Brock River Formation. Those are section 3 at the Copy location, and then the farthest west location at Adderback. And so already one thing that jumps out an observation is that the stratigraphy is so much thicker at the western end compared to the eastern end. There's also a lack of those thick mudstone dominated intervals between lower, middle, and upper Brock at that Adderback location. And associated with that, there's also a higher net to gross out there, lower net to gross or percent sandstone at the Copy location. And so it's with these observations combined then with paleocurrents that were collected in the field that we can really start to piece together the context of this really previously unknown basin. And we infer that sediments were transported, kind of shown by those arrows in the upper right, down into a trough-like basin at the junction of these 2 oceans. The Brock River Formation reflects more of an axial deep water lobe deposition in the west and more of an off-axis deposition, 70 kilometers corrected given the amount of shortening to the farther to the east. And then below that, at the very bottom, a chronostratigraphic diagram of the Brock River Formation shows hypothetical stacking of kind of the minimum number of lobe complex sets to satisfy the stratigraphic relationships observed by all of these stratigraphic sections. And so those colors correspond to those bodies shown in the map above there. And essentially, the basin shows that there was more aggregation early in the system, with compensational stacking of the system becoming increasingly the dominant driver of lobe architecture with time as that basin depot center accumulated sediment and evolved into a less confined and then lower gradient basin floor. Other implications of this work relate to subsurface studies of analogous systems, so other fine-grained, sand-rich, deep water, extensive systems. So to give you a better idea of the comparability of the scale to subsurface system, here's a 3 mile by 3 mile block, like a lease block, over the top of the scale of the initial fold limb that I keep showing. And this shows how this work really helps inform and fill in granularity between sections, or otherwise like wells, to predict how much or how little heterogeneity there is in these deposits and how extensive sandstone bodies may be. So now jumping to completely different implications of heterogeneities in deep water deposits and jumping from Neoproterozoic time to the modern realm, another implication of correlating deposits long distance relates to hazards. And I wanted to briefly show some work being done with Sultan Sylvester, Jake Cobalt, Joan Gomberg, and Lydia Steich in how turbidites are being correlated for paleoseismology. Now, I really wanted to bring this up briefly to this group because it provides an example where significant heterogeneities that exist in just more general deep water deposits should not be overlooked, but they are in some existing models. So the map on the left shows the Pacific Northwest of the US, so from offshore Northern California to Washington, and the locations labeled on the map correspond to locations on the y-axis of that graph. And on the x-axis, you'll notice age and then turbidites called out by those T's with numbers. And essentially, these deposits, these turbidites, have been dated. You'll see these are all radiocarbon ages. The bars show the significant uncertainty that's common with radiometric dating, but also the amount of overlap. And yet, a lot of these deposits where they exist, these individual turbidites have been correlated across this whole margin. So that's kind of what this is showing. Really ignoring whether that makes sense depositionally. And the significance of these correlations is that the current earthquake recurrence for the margin relies on such correlations, because really over such a great area, only great megathrust earthquakes can initiate turbidites synchronously. And yet this group can understand how it's quite difficult to infer synchronicity just by correlation of deposits alone, especially over such distances and over different depositional systems. So this is to highlight some other work ongoing between USGS and the Monterey Bay Aquarium Research Institute, just highlighting focus just for these purposes just on the southernmost part of the margin, as you can see in the map, where there have been new cores collected, adding granularity to understanding the depth of deposits down there. And then on the right, these are a suite of cores, modern sediment cores that were collected from the seafloor, showing CT scans and showing false color CT scans to highlight sand in yellow and mud and finer grained in the purple color. And right away, you can start to see how, even though attempts have been made to correlate turbidite 1 all the way down to turbidite 5 across, again, the entire margin, even though I'm focused just in the south here, there's too much variability to do so. There's way too much heterogeneity. So what we're doing is we've re-examined a small subset of cores across the margin to really look at the sedimentary facies in detail, which hasn't been done before. And in closely spaced cores that are several meters apart, the deposits correlate quite well. It's believable that individual turbidites are preserved in different cores that are closely spaced. With slightly increased distance, maybe 9 kilometers away in this case, correlating is a little bit more challenging. And of course, now jumping from one channel to another channel to maybe an apron or more of a fan environment, that becomes incredibly hard, even though correlations have been suggested between turbidites across these distances. So in addition to looking at the deposits themselves, finally, we are also testing the strength of correlations by automating a more objective correlation method. This is described by Zoltan Sylvester in his Sylvester 2023 paper. But essentially, we use dynamic time warping to correlate the density logs of these existing cores. And we calculate a correlation coefficient for sample pairs between each of the 2 log pairs. And by mixing in synthetic logs and correlations, we also calculate p-values, or essentially calculate the statistical significance of each of the correlations to test the chance that they're simply random. So what we're looking for in a strong correlation like this one here, where cores are only several meters apart, is a high R value, a low p-value, that it's not just random, and also that there isn't much deviation from the dynamic time warping correlation to the existing correlations of Goldfinger et al. Along the margin. So where the black dashed lines, those highlight where the dynamic time warping correlations matched existing correlations, and then anywhere it's red, there was a mismatch. And not surprisingly, with increased time or increased distance between cores, there's a lot more red lines or disagreement between correlations, and those statistical values are not strong. And point here really is just that not all deposits, and arguably these deposits, just shouldn't simply be correlated. So with that, thank you very much for allowing me to speed through 2 very different examples of deep water heterogeneities and the implications of, in one example, where too many assumptions are perhaps being made in how little heterogeneity can be seen in deep water depositional systems. But then another example in the Neoproterozoic fan system, where really relatively fine-grained, sand-rich, and uniform system is preserved in a pretty large basin. So thank you.
Thank you, Nora, for that brilliant talk. Absolutely fascinating to see this system pulled apart in such detail. I have a ton of questions. I'm sure lots of other people do, but we won't take them now. Please, if you've got questions, paste them into the chat and we'll handle them at the break. Right now, we're going to go straight into the next talk, which is going to be a recording from Jorge Torrico, which I'm sure I just mangled horribly, on structurally controlled deep water sedimentation on the Laurentian passive margin.
Hello everyone, my name is Jorge Torrico. I'm a master's degree candidate at Nora University and member of the Iberian Tectonostratigraphy Research Group of Dr. Wall. Today, I will talk about the Cohen group, a convertidation of autonomous strata that develops in Western New Zealand, Canada, and more specifically, I will talk about structurally controlled sediment transport and deposition on the Laurentian passive margin. The Cohen group is located in the Humber zone, which is the western margin of the Appalachian orogeny and constitutes the ancient continental margin of North America, the Laurentian margin. Recent studies of the regional setting and paleogeography of the Laurentian margin evolved, presenting a rift architecture model with rift segment zones, and the Humber zone is located within the long-range rift zone. The Humber zone is also subdivided into segments, and the Cohen group is located there in the middle. So we use species analysis and paleo analysis to investigate the potential influence of this rift architecture model on sedimentation and to look for possible links to coeval transform fault reactivation with events like rifting of the Ottawa and Saguenay graben. So the paleogeography of the Laurentian margin is related to the breakup of Rodinia that led to the opening of the Ayapetus Ocean in the more narrow Taconic Seaway. They both close with the onset of the Taconic orogeny around 470. The position of the Cohen group and the coeval carbonate platform that built up along the Laurentian margin occur between 500 and 475. And contrary to the carbonate platform, the position of the Cohen group occurred in a slope-toed marine environment. The Cohen group, the sedimentization of the Cohen group is characterized by interstratified limestone with shale and mudstone, but we also find some fine medium-grained sandstones, dolostones, and terts, mainly in the lower Ordovician succession. But today we will focus on the more coarser material, on the conglomerates and sandy limestone beds, which show wave-like structures. So on the field, we characterize the conglomerates based on their support mechanism and fabric, if any. I will start with this mega conglomerate, which is characterized by meter-scale large white algal boulders that are supported by locally derived clasts, and the bed shows a non-cohesive matrix, indicating or suggesting a short distance or a short transport distance. And if we relate this to a gravity-driven depositional process, we interpret it as a debris slide or slump. Then we have this form class-supported conglomerate with visible fine grain matrix and a chaotic arrangement of the clasts, which we interpret as a slump or debris flow. If we continue with the fluidization process, we have this scour-filled class-supported conglomerate with slightly aligned clasts, which we interpret as debris flow, and then we have this normal graded class-supported conglomerates with a visible greenish-gray muddy matrix in these pictures, and with clasts with imbricated clasts aligned along the axis. We interpret these beds as debris flows or deep currents. And finally, we have this matrix-supported normal graded conglomerate with a clear cross-stratification that the top, and it is interpreted as a turbidity current. So we also observed in the fine to medium grain sandy limestone beds a wave-like ripples occupying the TC interval of Palma sequence. And these beds are, of course, interpreted as turbidites. And in the coarser material, in some conglomerate beds, we observe the hammock-like structures with typical hammock and whale forms. So we have wave-like structures mimicking wave ripples, dams that can be related to frequent bank collapses, storms, and waves that occur in a shallow marine environment. However, the wave action is unlikely in a slow-flow deep marine environment, as it is the case for the Coalhead group. So we looked for analogies, and we found some studies from the Alps and Pyrenees that describe these wave-like structures due to the fact that the turbidity currents reflect on fault or against fault scarps, resulting in the development of internal shear boundaries and propagation of oscillating currents to the bed during the acceleration of the turbidity flow. So since we're talking about flows, we measured some paleo currents along different outcrops in the Hamburg arm Lockton, and we obtained a main paleo flow direction towards the south, suggesting a structural uplift to the north, a potential fault. So we can conclude that we have independent observations such as the non-cohesive boulder conglomerate, the wave ripple structures in the sea interval of this turbidite, and the main paleo current towards south that suggests fault reactivation and basin confinement during the deposition of the coalhead, consistent with the existing reef architecture model of the Hamburg zone. For that reason, we suggested the occurrence of a transverse fault here in the north part of the basin. And in terms of the timing of these events, when these deposits occurred, we observed these deposits all along the coalhead group, but most of them were deposited during the Laurentian, the microscope member, and they are all cut by the boulder horizon, boulder conglomerate, the camber division boundary at the base of the sterile member, implying active faulting coeval to similar events like the Saguenay and Ottawa ravens. So I thank you very much for your attention. Questions?
Okay, so we won't be taking live questions for Jorge because he's not actually present. He's actually traveling to the EGU right now. But you can ask questions directly of Jorge. We're going to be, there it is. His email is in the chat there. So if you've got any questions on this topic, you can email him directly. Next up, we have another recording, this time from Jungang Pang, who's an early career researcher at the Xiaoyu University in China, who's going to be talking about the facies architecture of deep Lacustrine fan successions in the Triassic Yanchang Formation in the Ordos Basin. So let's see if we see any differences between lacustrine and marine turbidites in this talk.
Hello, everyone. My name is Jungang Pang from Xi'an University, China. I feel very honored to have this chance to communicate with all of you. My title is Facies Architecture of a Deep Lacustrine Fan, an example from Ordos Basin, China. Objectives to provide a classification scheme of lithofacies and lithofacies association for deep lacustrine turbidite strata of the Yanchang Formation, identify different deep lake channel and low soil environments. Finally, to construct a deposition model. And location, here is the location of Ordos Basin in the map of China. And here is the location for these outcrops and drilling wells. And here is the Yanchang Formation strata. Our classification scheme of the lacustrine sedimentary soil environments. We can identify the deep lake semi-deep lake, shallow lake shore in the order of decreasing work depth. Deep lacustrine fine or top depth may be developed in this zone. This is identifying the deep lake and semi-deep lake extents of the Yanchang Formation. It migrated southwest and then northeast. Here is deep lake shells and top depths. The deep lake migration in profile. Lake facies classification scheme of deep lacustrine fine. We identified the following facies, for example, SMT, SM, and so on, and compared with these facies with unites in formal sequence. And this here is the depositional interpretation. Here is architectural elements identified in Yanchang Formation. For example, mass transport deposits, slope channel top depths, channel lip top depths, and composed of fine channel top depth, lip top depth, loop, shade, and so on. Here is an example of deep lake top depths in outcrop. The following characteristics for these architectural elements in outcrop. Here is the slope channel top depth. We can identify this side-dominated channel field developed in slope setting. We can find this concave base and flat top shape, and all kinds of soil marks. For example, groove cuts, float cuts, and rip up mud class in sandstone. And alternatively, we can identify this mud-dominated channel field. Channel lip top depth. In this outcrop, we can find it mainly composed of fine channel top depths and lip top depths, and some characteristics in detail. Fine channel top depth mainly composed of sandstone, overall fanning and seeping upward, and all kinds of sedimentary structures. For example, massive normal graded bedding, asymmetric ripples, planar bedding, various soil marks, rip up mud class. This is the depositional products of high density crates, late top depth, fine grained sediments. We can find this is a product of low density of the crates, low top depth, fine to medium graded, medium bedded, and clearly sink bedded, massive and ripple sandstone unites. We can find claims, load cuts, float cuts, and so on. And also can find this causing and sinking upward trend. This is the product of sand-rich and high density of the current, modified by subsequent traction currents, and occasionally find these hybrid event finds. We can extend this approach to basin world subsurface data science, and from the procedures we can find vertically stacked channel top depths are common with significant thickness and lateral extent and continuity. Vertically stacked loops are also common, but not in sync. Slope channel top depths are found or identified locally. Here is the distribution of sedimentary feces during Chang 7. The component factors for the development of the lacustrine top depth finds from the following depositional indicators. We can know slides and slabs in the slope break zone triggered by volcanic eruption and seismic events are the main mechanisms promoting density flows to deep lacustrine finds. Yeah, for example, we can identify the slope break zone in the plane view maps or in profiles and tough liquefaction flow or sliding flows. The visual model, the extension and orientation of sand bodies in shallow and deep lacustrine settings are characterized. They are mainly triggered by clefts in slope break area, and deep water depth sand bodies are widespread, and different architectural elements in these 5 paleobathymetric zones. Here is a conclusions. That's all. Thank you very much.
All right. No, again, an excellent presentation, and please do post questions in the chat for all the individual presenters, but also after Zane's talk, we will be having a kind of a more general committee guided question session. So now we're going to, again, in the theme of diversity, we're going to go from deep lacustrine fans, and Zane Jobe's going to be talking about carbonate deep water systems, deja vu or jamais vu, to see if, again, what can we apply to carbonate systems? What learnings can we extract from those to apply back to clastic systems?
So I don't, Fabian knows French, but I don't know French. But I Googled what deja vu and jamais vu mean, and I've had both of those looking at these types of carbonate deep water systems. So this is a talk where I don't really have many answers. I have a lot of questions, and so I'm looking forward to some of the discussion here. And I'm just going to show a bunch of nice photos without a whole lot of without a whole lot else. So just in case you don't know what these two words mean, which I kind of didn't. So deja vu is like the feeling that you've seen something before, right? Like something unfamiliar sort of can look familiar to you, and jamais vu is like a little bit the opposite thing, where you something that is familiar to you all of a sudden seems unfamiliar, right? So like for example, if you look at the word calciturbidite and you look at it over and over and over and over, or you write it over and over, all of a sudden you wonder if you're misspelling it, right? That's the like jamais vu. So I've definitely had both of these feelings here. And before I continue, I'll just thank my co-authors here, Arnaud, Leslie, Perrette. We have a big group of students here that are doing great work. Most of the work that I'll show you is theirs. We have a lot of really great industry and academic collaborators as well. I'll shout out James Bishop and Brooks Ryan and Ted Playton and a few others as well. So in any case, this is so I'll show you some things that sort of look familiar, or that I think look familiar coming from a clastic background into the carbonate realm, and then I'll show you some things that look kind of weird. So and then I'll be happy to take take some questions. So what does seem familiar are places where you can find normal looking deep water event beds, right? So sharp based units, right? Like you see a more muddy unit here, nice sharp base, coarser grain clasts, and those clasts sort of fine upward in a structureless sort of bed. So those things look relatively familiar, and they have thicknesses that are that you're used to sort of seeing from a clastic or I should say siliciclastic sort of frame of reference, if you will, right? And these are all most of the images that I'll show you are approximately at the same scale, right? So these look familiar. There's also some things that seem to sort of have siliciclastic analogs as well. So here on the right-hand side, this is a person. It's actually Anna Bernhardt, who's going to give a recorded talk later in the session. So that's she's blown up, right here, and so you see it's really sort of thick class-supported conglomerate at the base going into a matrix-supported conglomerate. And these are probably some sort of like epic, hybrid event bed. And so here's a student, Maxi Miguez, here for scale. And these are some units that we're working on now that actually look, relatively familiar to that. So about the same scale of thickness. You can see some of the really large class here, a sort of overall increase in the matrix. And I put that in air quotes because we'll talk about that here in a second. We see things that look the same sort of architectures, things like channel margins. So here's a nice erosional surface here, right, coming down through, through here, cutting out this sort of thicker bedded conglomeratic unit, cutting out these thinner beds. This is all carbonate. There's not a single quartz grain in this. And then here's an example where this is mud and sand, so siliciclastic mud and sand, and then this is conglomerate here. So you see the same sort of architecture there as well. So there's many things that that seem relatively familiar. And the last thing I'll show you that seems familiar is maybe a kind of a peculiar one, but one that we've seen in similar or in several places rather, and that's these what I like to call like a bulldozer. And so this is some sort of erosional feature where the base of this turbidite bed is actually coming around this way, and it's sort of bulldozing down and eroding, kind of creating a flap of thin bedded, more muddy sediment. So we see this in the clastic realm. This is from Pigeon Point in Northern California, and we see the same sort of thing. It's a little bit harder to see in these carbonate systems because the way they weather, but you can see here that's the base of this unit. So these little churty thin beds here, right? That's the same sort of thing. So you're peeling these thinner beds up and incorporating them into some of these flows. So having sharp-based event beds that are sometimes erosional, sometimes not. So those sorts of things seem relatively familiar. Some of the architectures I think seem familiar. I won't show you some of the architectures today that seem a little bit different. James Bishop published a paper last year that sort of focuses on some of those from the Sacramento Mountains. But we'll talk about some of the issues in dealing with carbonate systems here, and then I'll show you some things that sort of look kind of weird. And so for example, the sort of classic carbonate, the classic carbonate textural descriptions, like a Dunham description, right, is to call things by their matrix or grain support. And for process sedimentology, right, like the composition of the matrix is a key a key fact or a key piece of data, I should say, to making those interpretations. And so if you have a wax stone, wacky stone, for example, that can be sort of in situ faunal growth. That can be a sort of very dilute turbidite, or it could be some sort of debris flow. And so if you just say it's a wacky stone, that doesn't really help you with the process description. However, conversely, I think if you don't understand the carbonate textural descriptions and the diagenetic implications of those, then you really miss the boat in trying to infer process from that matrix, for example. So so that's you really need some help with the diagenesis, or you need to really know that stuff really well. And those methods, I think, for doing paragenetic characterization for a dyed-in-the-wool siliciclastic deep water person, right? Nobody's used to doing those sort of things, right? And so you sort of have to reevaluate your toolkit when you start working these kinds of rocks. So there has been a lot of work done to solve some of these types of problems. So the sort of key reference here is this one from several years ago in sedimentology. And their recommendation for dealing, especially with these coarser grain systems, is to characterize the sort of the grains, the larger class and the matrix individually and separately, so that you can make those kinds of process interpretations. So in any case, this is a really nice paper that discusses that. So one of the other issues is that when generally, I think when carbonate folks talk about mud, or talk about matrix rather, they think of mud. And I think when more process sedimentology people talk about matrix, it's just what's in between whatever is bigger grains around those smaller grains, right? And so there's, I think, a little bit of confusion about what matrix, really is in some of these systems. And when you get into mixed systems like in the Permian Basin, then that gets even more complicated when you're trying to think about what what the geomechanics of the matrix are, as opposed to the larger class around them and those sorts of things. So in any case, Dunham back in 1962 said mud was anything greater than, or rather less than 20 microns. Wright, Paul Wright in 92 said 60 microns. This paper here says 63 microns. Wentworth back in 1922 said 62.5 microns. So this is based on a log 2, the phi scale or the psi scale, as Gary Parker likes to, to say. So mud really isn't even a grain size at all, but it sort of gets conflated with silt and clay, and then conflated again with matrix or shale in this case. So I think there's a lot of terminology issues that we can try to solve over the next several years. And then I just have like a screaming face when you get into mixed lithology systems, where things get relatively messy. So in any case, yeah, the matrix is important for inferring that process. And so here's a bed, sort of normally graded unit. And so in blue, right, we usually think about, like, I would approach this to say, like, okay, well, I'm going to look at the grain size characterization of this to infer the process. And so I'm like, okay, well, there's the base and the top of that unit, and it's generally sort of fining up, and maybe you can draw some internal boundaries in there, as well. And but to really figure out what that process was to generate that, you need to understand the carbonate texture and the diagenesis. And so, this would be like a rudstone or a floatstone at the base, for example, and then grading up into sort of packstone, waxstone, mudstone at the top. There's also, the sort of fracture characterization and the diagenetic characterization comes into this as well, where, that chert nodule wasn't there when that was deposited. Neither were these little stylolites, that you see here. So how much pressure solution happened and how much thickness did you lose here? That sort of affects the way that you're going to interpret the process here. So so these are all things that coming from a sort of siliciclastic sand mud system, generally people aren't too worried about. But there are definitely things you have to take into account when working these kinds of systems. Okay, so yeah, so this is what you would sort of normally look at, right, and say, like, oh yeah, this is just a nice little normally graded sand bed. Well, there's no sand in here. These are all carbonate grains. You can see some nice bryozoa and brachiopod and some fusulinids and sort of some chertified sponges and then some chert nodules here as well. So if you take this and you slab the sample, then what you get, I'll make this disappear now. What you get is this. You get a much more clear view of what's happening with the grains and with the matrix here, right? And so if I zoom in just on this one, for example, right, that's here. And so, by the way, these are centimeters, so this is about a 10 centimeter thick, bed, or maybe 15. So you can see here the smaller grains. These are all, the smaller matrix in this case is all grains, right? There is a grainstone, and so that was very likely deposited grain by grain deposition by a sort of an organized, more turbulent flow. There's no mud in this matrix, right? And sometimes diagenesis can complicate that. If you dissolve some of those out and redeposit micrite, then it looks muddy, but you can usually see ghosting of the grains when you have these sort of resolution, either of polished slabs or of thin sections, both of which I think are required here. So so in any case, if you do some quick grain size picking here, and so Arnaud Slootman did this, and then Viska Dewey, who's a master's student here, is going to be working a lot more on this over the next little while. You can separate the sort of larger grains. That's what's shown in red and green here. That's these sort of larger class. You see that they're overall normally graded through the bed, although you could argue about the trends in here. There's also issues with the effective density of different types of carbonate clasts, which have intraskeletal porosity. And so David Nori, who's a PhD student here, is working quite a bit on some of those things. So for example, these big rugose corals, they might have been lighter hydrodynamically than these sponges and other lithoclasts, right? So they would float relative to their true grain size, right? And then in the blue, you can barely see it in here in the blue. That's that little stripe in the center of this. That's this data, right? So those are all the grains that are here. And then there's a histogram of the grain size. It's probably a little bit too small to see, but this is like medium sand and this is silt, okay? So indeed, even the matrix here, the matrix, quote unquote, which are grains, yeah, they're normally graded. And so that really can help you with these types of process interpretations, but you really have to sort of get down into the, into the weeds to really understand those things. Yeah, and you need some real microscope work to confirm that the matrix is what you think it is, right? So in any case, so that's a sort of I guess a primer for what I'm going to leave you with here, which is stuff that I really am not very sure about, which is it's kind of fun actually. So here is a siliciclastic mud and siliciclastic sand bed from the Chlordorm formation. These are Ordovician rocks in Quebec, and so these are what we interpret as some sort of hybrid event bed. And you can see it's sort of more sandy in the bottom and more muddy at the top with lots of big mud clasts. And so it's sort of classic, I guess the HEB sort of Houghton, sequence here. I think we see similar stuff in the Wolfcamp, for example, in the Permian Basin. And by the way, these are all at approximately the same scale also. So there's a core, from that system. This is from Saskia Putri, who has a paper in review right now on these rocks. And you can see some of those pseudonodules and things here, which are pretty typical in these, like what she's interpreting as an H3 division. And then, here's an example from some current work that we're doing. This is from Sanjar Begambietov's work in New Mexico. And so you see a nice sort of a more muddy unit. This is all carbonate again. More muddy unit, nice sharp surface here, and then you see something that sort of looks like this sort of mud clast and sort of sheared textures that look reminiscent of these sorts of things. So we thought like, oh man, we're going to carry this whole big piece down and make some slabs and make some thin sections. And so so we did that, and you can see some of the sort of Dunham, the Dunham textures here. And so we took a giant, like a postcard sized thin section from this area. Arnaud has a contact in Germany who makes the most amazing thin sections that you've ever seen. And that thin section is here, right? So this laminated unit on top, that's this stuff here. This sort of sheared looking texture, that's what you see in here. And then the lower, we don't get the whole part of the bed. There's actually another thin section down here that I won't show you today, but that's this unit down here. So I'm going to blow this up so you can see it a little bit better. So it's 10 centimeters by 15 centimeters, right? That's a single thin section that's that big. And so we're sort of currently working on a whole suite of these thin sections here. So in any case, that's what this looks like. I won't interpret it now, but I'd be happy to hear what everyone what everyone thinks about some of these examples in particular. So in any case, so I think moving forward, I think these systems, like there's some deja vu and there's some jamais vu, right? So there's some things that look familiar and there's some things that don't look familiar. And I think if we're careful and we describe things the way we see them, and people that don't know about diagenesis have some diagenesis help, I think we can solve some of these problems. But I think some problems are mostly solved already. But if you don't have the background in this, you might not have read the papers yet. I certainly hadn't read these papers before embarking on some of these new projects that we're working on now. And the last thing I'll say is, coming from like a siliciclastic background, like there's always this like, oh, it's like those carbonate guys over there, and it's not really, it shouldn't ever be us versus them. And I mean, I think some of the rocks that I've showed you today are extremely interesting from the process sedimentology perspective. And I think deep water carbonate systems generally are sort of understudied compared to siliciclastic ones. And so I think there's a lot of work to do there. And so that's, pretty exciting for, for lots of, lots of investigators and lots of students to have projects and publish cool papers and figure out interesting, questions. So in any case, I'll leave you with a video of some flume experiments that like I said, David Nora is working on to look at shape, grain size and grain shape, and grain density characterization in natural carbonate sediment. So this is sediment from the Red Sea that's been that was collected by Arnold Slootman and John Reimer, and they were nice enough to let us use this to conduct some experiments at Utrecht University. So in any case, I'll leave you with that, and happy to take questions during the discussion.
All right, thank you, Zane. Again, another super interesting talk. And yeah, to your point, there's siliciclastic, there's carbonates, but a lot of the processes may be the same, a lot of the processes may be different. And carbonate sedimentologists looking at clastics and clastic, siliciclastics looking at carbonates can again help us get that different perspective. So now we have some time for questions right now. I see a few in the chat, so if y'all haven't put any in the chat, feel free to do so, because again, if we can't address them here, we'll be able to address them, send them all to the speaker so they can address them. But the first one that did pop up is kind of open to the panelists, that all the panelists, not just the ones that have spoken already, but it's from Jason Flom. The question is much of the focus is on the variability in the coarse grain deposits related to the variable sediment sources and sea level. So is there any evidence that fine grained units are also related to up-dip sources, or are they transported by deep water geostrophic flows with sources from other up-dip sources? So I kind of want to play, if you're one of the panelists, feel free to unmute yourself. And if you can't, we can unmute you to answer that question or provide some context. It's an interesting question.
I'm unmuted already, so I can start. Yeah, I mean, we've had a lot of these kind of discussions in the field over the last couple of years, and so I think certainly there are lots of examples in the modern carbonate, the modern carbonate deep water systems where contour currents, bottom currents play a large role in redistributing sediment, and so the Bahamas are a really great example of that. Like, you can get these big thick mud wedges on one side of the island, and then there's nothing on the other side because it's being removed from that side, or sort of windward leeward issues. And so I think some of the recognition criteria for distinguishing those types of deposits from downslope directed sediment gravity flows, I think is still sort of ongoing. And I will say too, like I saw in, and I meant to say in my talk that, a lot of these things that we're looking at, man, the stuff that Jorge showed looks so similar to what we've been looking at, which is cool. But he showed a lot of paleocurrent data, and that's something that, coming from the siliciclastic realm, I mean, I measured so many paleocurrents in lots of siliciclastic rocks, and man, let me tell you, it is hard. It is hard to measure paleocurrents in these carbonate rocks because the way they weather and well, mostly because of the way they weather. And so in any case, yeah, I think we need better recognition criteria, and we need to figure out how to measure paleocurrents in these systems, at least in outcrop.
Interesting point. I think in a way, it also kind of aligns with some of the things that Nora was saying in her talk. Just that question of understanding time correlation versus depositional system correlation too, right? Because if you can start correlating things that she was showing off the west coast of the U.S., you start to question how certain things can correlate like that when we have an understanding that the processes might also be varying actually within that. So I think just the question in general, you could almost reframe the question as, are we constantly biasing ourselves when it comes to thinking up dip, down dip, and when we're interpreting everything. Obviously that's, a good place to start, but we have to have that understanding. And again, how does all that get further complicated by those finer grained flows that might be happening in multiple directions? So Zane, you're unmuted, and there's another question that came in from Howard Feldman. He was wondering, how can you have carbonate debris flows if, he thinks carbonate mud doesn't have cohesion?
Yeah. So there's been some really interesting work, and I hope Jaco is on as well, because he's been kind of at the forefront, of this. And so what he's done, and I don't want to steal his thunder probably too much, but they've been doing experiments using kaolin and other types of siliciclastic mud, and then also carbonate mud, at least sort of like crushed carbonate mud. And what they found was that it's not as cohesive. I think what John Reimer would say from my discussions with him is that the organic matter that is always associated with carbonate mud is quite sticky. So what he says is like, well, go out on a carbonate bank, a muddy carbonate bank, and go try to walk around, see if your legs don't get stuck. So I think it can be very, very, it can have a lot of cohesion if it's, if it has a lot of organic matter. And so, but again, when you're looking at Permian or Mississippian rocks, or, something that's clearly had a lot of diagenesis, figuring out what that mud originally deposited in the matrix, or was that an open pore space that was then occupied by a cement, by like some kind of micrite. And so those could be pretty tough questions, I think. And so that's why we've been resorting to some of these what seem like ridiculous, like grain size profiles through single beds. But it's really to try to figure out, some of those kinds of questions. Yeah.
Nice. Excellent. From any of the, go ahead, Stan.
Yeah, no, I was just going to say, I think you're terribly brave taking on these mixed carbonate clastic type systems. I've attempted to do this myself in the past, and it just quickly gets into the screaming face mode. I was also going to comment. You're clearly already aware that I saw Jaco talking about using different types of grain morphology back at the Bauma conference last year, and he had some very interesting insights there. So I'm looking forward to hearing more about that as we go. I do want to turn to Nora's talk briefly and ask a question about that. Well, it's a comment and a question. Nora,
hey, Stan, before I move on, I think there was, I think Sharma had a comment on some.
One more. Yeah, do you want to ask the CCD question?
On some of the cohesion stuff, yeah.
Yeah, go for it.
Yes, all right, just wondering on the dissolution of carbonates in deep water. Is that common below the CCD, and how that affects reservoir properties? That question?
Yeah.
Oh no, it was someone was saying that they could contribute to this the cohesion question in carbonate mud, I guess.
Oh, go ahead.
Yeah, that was me, Zane.
Oh.
Jaco here. Yeah, you might be interested to know in the audience as well that we did some experiments with carbonate mud in different types of sediment gravity flows, and it is true indeed that if you consider the mud only, and that is clay size to silt size, that's what we investigated. It's not cohesive, and in fact, it's even less cohesive for some reason, and we don't know exactly why, than siliciclastic material of the same size, because it's more mobile than siliciclastics. However, biology is really important in carbonate systems, as you already mentioned. So there's all kinds of sticky biological polymers that, although the mud itself is not cohesive, that makes the mud cohesive. And the jury is still out, really, whether that biological factor is as important, or perhaps even more important, in carbonate systems than in siliciclastic systems.
Excellent. Go ahead, Stan. I know you had a question.
Yeah. Okay. So I wanted to turn to Nora's talk on the Zerinse from earlier in the session. It was very interesting that the panel here were having a bit of a side discussion whilst we were talking, all remarking on the extraordinary lateral exposure and vertical exposure of those outcrop systems. For myself, I first saw them a couple of decades ago in some photographs by Schwartz and others, and I've been using it ever since. Every time I get a question for anybody, can turbidite systems really be this laterally extensive? I just show them these photographs. They're absolutely perfect for that. Which got me thinking, and using them as an analog for subsurface lobe systems. Have you attempted to convert your grain size profiles into gamma ray profiles to make it more comparable to subsurface systems? I'm sort of assuming that taking gamma ray at the outcrop wouldn't work because they'd be too old and too indurated.
That is a great question. Thank you for that, Stan. The short answer is no, and it is related to difficulty in actually measuring the grain size, and because they're so metamorphosed. So these are grain schist grade metamorphosed rocks. Fine-grained sand is the coarsest that is really in the system, apart from some erosive bases with gravels. But it's been kind of an estimate, a best guess at grain size, unfortunately. That said, the fine grained nature of the grain size in general, and then also existence or presence rather of some hybrid event beds or transitional flow deposits based on observations that you can make in relative grain size differences and mud content, and how that pops up in thin sections that were taken, have made it comparable to certain systems, I think, that can be treated as analogs. So I do think, and I've chatted with a number of colleagues about this for years now, that I think it offers a good analog for the Wilcox Formation, given its extent, given its general grain size, sand content, but also presence of some transitional flow deposits. But no gamma ray data or even generated estimated gamma ray.
So you've correctly estimated where my question was coming from, having spent some time working on the Wilcox. These highly laterally continuous systems of very fine grained kind of nature. Okay, thank you. That was my question. I think we're just about out of time for the discussion here. So we'll take any further questions, I think, into the next discussion break. So for the sake of everybody's bladder, we're going to take a 5-minute break here now. We'll reconvene at 1:45 the hour. No need to sign off, just leave your microphones open. We'll be back in 5 minutes and we will start with the next presentation.
Excellent.
Oh, and I should say, Cassie, if you don't mind, we'll be launching a short poll for everybody, just a couple of very quick questions for you about the SEPM and these meetings.
Excellent. All right, we'll start when we come back.